Well, believe it or not, we're already starting chapter 13. Vector valued functions. But first, I'm going to start with something that hopefully you've done before, Math 3B, parametric functions. So a parametric function, an example would be x equals something, y equals something. And the para refers to a parameter. So both of these are going to depend on a parameter t. Basically, like as time goes by, the x is going to change and the y is going to change. In this case, I'm going to use sine of t, cosine of t. So right now, it's just in 2 dimensions. And because it's in 2 dimensions, I can use my old-fashioned graphing calculator. I was practicing before you got here. So in case you don't remember, go to mode, put it in radians, and then also move over right here, make it parametric. Now when you go to y equals, it's going to say, well, what does x equal and what does y equal? And this key right here now is going to be a t. For some reason, Texas Instruments likes to use a capital T. Nevertheless, it's t. When you take a look at the window, since it's a trig function, go from 0 to 2 pi. And then I made this a 0.03. Usually it's like a 0.13 or 0.12. I just made it a little bit smaller so it'll graph more slowly. And then sine ranges between -1 and 1. Cosine ranges between -1 and 1. And then what's the shape? Oh, hold on. Let me just change a number so that it'll regraph it. So if you change any number, it's going to have to regraph it. And then watch the graph. So it's going around. You can even see the little circle leading the way. Hey guys, let's go around this ellipse. Except it's not supposed to be an ellipse. It's supposed to be a circle because this is going from -1 to 1 and -1 to 1. So that is a circle. And it went this direction. So when you put arrows on it to show what direction it's going, that's called the orientation. Now this doesn't look like a circle because the screen is actually a rectangle. So every graph you're looking at has actually been pulled sideways. If you want to adjust for that, go to zoom, square. And then it will square off the screen, and now it should look like a circle. Okay, so there it goes. By the looks of it, it looks like it's going at a constant rate. Not sure how accurate that is, but it sort of looks like it. Okay. Now, what if you wanted this in rectangular coordinates? So rectangular coordinates means good old x and y. Well, because this is a circle with radius 1, I know that the equation is x squared plus y squared equals 1. Or I could have gone over here, squared both sides. That would say x squared equals sine squared. For this one, square both sides. Y squared equals cosine squared. And then add those up. On the left side, it's going to give us x squared plus y squared. On the right side is sine squared plus cosine squared, which equals 1. So there it is in rectangular coordinates. The directions on the homework might not say rectangular coordinates. It might give you something like this. Or, hold on. I need to hold on to that sentence. So you could also have it as a vector valued function. So it's the same function, the same graph, but vector valued function will look like this. R is a function of t equals this vector. The first component will be sine of t. The second one will be cosine of t. Okay, now in the directions of the homework, they may give you something like this. And then they'll say, rather than saying change it to rectangular coordinates like I did over here and here, it might say change this into a function of x and y. So the first thing I would do is say, okay, that means x equals sine, that means y equals cosine, and then do this magic, and then you've got a function of x and y. Now, this is a vector valued function, which basically means at any point, so as the object was going around a circle, at some point it was right there. When you only have this, the rectangular, all that tells you is you've got a circle. You don't even know which direction it was drawn. When you have parametric, then you have the idea of time passing. So as time passes, this thing went around the circle in this direction. So with parametric, you have a little more information. Then with the vector valued function, you not only have that parametric information, but you don't see the vector pointing to it, but it's basically a vector pointing to it and says, I see the point, it's right there on that circle. So you even have a little bit more information. Now, what about if we take the derivative? So you just go to each component and take the derivative. The derivative of sine is cosine. The derivative of cosine is negative sine. If this is the position function, then this is the velocity. So, for example, what is the derivative at 0? So the derivative at 0 will equal cosine of 0, comma, negative sine of 0. So the velocity vector at time 0 is going to be cosine of 0 is 1, sine of 0 is 0. So it gives us this vector right here. Now, remember, when it started right here. So what does this vector mean? So this vector means go over by 1 and then 0. So this vector is actually like this. But because we took the derivative, that tells you the tangent. So it can be interpreted as the velocity, but it also tells you the tangent. Well, as I've said before, the placement of the vector doesn't matter. This is the actual vector. As long as you keep it the same length and put it up here going the same direction, then it's the same vector. So that right there is the tangent vector. So as this thing would be going around and around, as it gets to this point, basically, if you think about like in track and field, there are hammer throwers. So they have a wire. On the end of the wire is a weight, and they spin around really fast, and then they let go. And if they were spinning like this and they let go at that moment, that's the way the rock would take off. Of course, gravity would take over after a little while, but the moment that the person lets go, this is going to be the direction that it would be going. And if you find the length of this vector, that would give you the speed. So what would the speed be? So the speed would be the length of this vector. And that would equal 1. So this is the speed, and this is the velocity vector. Okay, what about the second derivative? So take the derivative of the first derivative. So the second derivative is going to be the derivative of cosine is negative sine. The derivative of negative sine will be negative cosine. And so the second derivative, and again I'm going to use 0. So that would be sine of 0, which is 0, Cosine of 0 is 1, but then it's got this negative. So what is that? So that vector actually goes this way. 0 for x and then negative 1. So it's going straight down. But again, if the object is right here, you can take that vector, copy it, and paste it right here. So the acceleration would be going like this. Now, think of this as the hammer thrower again. As that person has the weight spinning around and around and around, if they're spinning around and not letting go of it, that means they have to be, however hard that thing is trying to accelerate out, they have to pull in with the same amount of force in order to keep it around in a circle. Also, notice right here that the acceleration vector and the velocity vector are perpendicular to each other. Okay, so I'm basically trying to do all of the homework questions with this one example, and then I'll go and do some more examples. So the next part, still using RT is equal to sine and cosine. Find the equation of the tangent line when t is equal to pi over 4. So for the tangent line, that means use the first derivative. So the first derivative is cosine. For the derivative of sine, the derivative of cosine is negative sine. And then substitute pi over 4. So how much is cosine pi over 4? And how much is negative sine pi over 4? Perhaps you have the unit circle memorized. I don't, but I do have a calculator. It's in radians. Excellent. So how much is cosine of pi over 4? So that looks like it's the square root of 3 divided by 2, I think it is. The square root of 3 divided by 2. No. What is it? So if it equals that, and I square it, oh, it's the square root of, okay, so it's coming from the square root of 2 divided by 2. Is that 0.707? Okay. So this one is square root of 2 divided by 2. And then what about negative sine pi over 4? That's the same number except negative. Now let's go back to the graph. So here's the graph, and if you put trace and pi over 4, then we would have the x and the y coordinates, which happens to be pretty much the same numbers. So this is the derivative. That was going to be a sloppy R, sorry. The derivative. And then the point, that was 0.707, so that's square root of 2 over 2, and positive square root of 2 over 2. Now for the equation of a line in Math 3C, you go x equals, y equals, and if you're in 3 dimensions, z equals. The equation of a line will be something times t plus something, something times t plus something. And then what goes in front of the t? This vector. So it's going to be square root of 2 over 2, and then this one would be negative square root of 2 over 2. And then the point goes right here, square root of 2 over 2 and square root of 2 over 2. Now I want to test that theory. So if I also graph x is equal to the square root of 2 over 2 times t, and then plus the square root of 2 over 2. There's the x part. And then negative the square root of 2 over 2. T plus the square root of 2 over 2. Then, does that look like the tangent line? So right now, it only drew half of it. So that was the correct point, but it only drew half of it because if I wanted to draw the whole thing, I'll need to change the window and go from like negative pi to 2 pi. So now it's going sort of slow. Oh, in case you didn't know, when you're graphing, this little circle will be working. That means the calculator's working. If you want it to stop, just press on. So on will stop it. And then I could speed this up, make that like a 0.12. So that'll speed up the story. And then right there, you can see the tangent line, that little red line. Excellent. Okay, I'm still working on the questions that they ask in the homework. And another one is, oh, you know what? I already answered that question. The next one they ask is, what's the angle between the acceleration and the velocity? I already answered that one. That's 90 degrees. Okay, so we did that one. All right. Now what about 3 dimensions? So R now is going to have an X, a Y, and a Z. So if I start off the same, but now I need a Z component. So that's going to be right here. What if it was a 1? Well, from the previous one, I know that this makes a circle. And then this is saying Z is always equal to 1. So what that would mean is, in 3 dimensions, you go up to a height of 1, and then this is going to create a circle right there at a height of 1. Okay, pretty cool. What about if it's sine of t, cosine of t, and then t? So what if you change this last one to the parameter t? Well, at the beginning, when t is equal to 0, so the height would be 0, sine of 0 is 0, so the x component would be 0, cosine is 1. So that means it starts right here on the y-axis, where y is equal to 1. Now, because of this, it's still going to be going in a circle. But then this is going to make the z value get bigger and bigger. So rather than like this one, which just goes around and around and around and around, and you get the idea. It's going to go around, except this is going to make it go up at the same time. So now it's going to go around and around and around, but the z value is getting bigger. So it's like a coil. All of these are supposed to be the same size. Sorry about that. Anyway, so it's like a coil or a spring. So for this one, find the velocity vector at the point 0, 1, 0. In other words, right here. So there is no restriction on t being positive or negative, so it actually would coil down also. So as it went through this point, then what's the velocity vector? Well, it should be tangent to this. And because it's going up and going this direction, I'm thinking it's like that. except since I didn't actually graph it, the coil might actually be going the other way. But the way that I drew it, that's the way the velocity vector should look. But we can test out my theory by actually taking the derivative. So the derivative, that's easy enough. Derivative of sine is cosine. Derivative of cosine is negative sine. The derivative of t would be 1. Now, what do I plug in for t? This is not saying plug in a 0 right here, a 1 right there, and a 0 right there. This is saying you're at this specific point, but this t means, well, what time did you get there? 10:30? Midnight? Well, if you compare this to this, it's saying that this one has to equal 0, this one has to equal 1, and this one has to equal 0. So that means that t equals 0. And sure enough, if you take 0 and plug it in there, it's going to equal 1. If you take a 0 and plug it in there, sine of 0 equals 0. So this part right here actually means t equals 0. So take the derivative and plug in 0. So that'll be cosine of 0, negative sine of 0, and that's just a 1 no matter what. So this is going to be cosine of 0 is 1, sine of 0 is 0, and then this would be a 1. So that would mean in the x direction, go over by 1. In the y direction, go 0. And then in the z direction, go 1. So it would be like this. So that means when I drew this, it's actually going this direction. So I should have drawn the coil instead of going this. Because I'm right-handed, I like to write things that way. I should have gone this, the coil should have gone this direction. That's what this is telling me, that this little guess right here actually should have been going that direction. Okay, now for a question that comes straight from the homework. So find the velocity vector, and now as a product of its speed and direction. So the speed, that's just the length of the velocity vector. So the speed will be the length of this vector, which will be the square root of 1 squared plus 0 squared plus 1 squared. That's going to be the square root of 2. So rewrite this vector so that it's a product of the square root of 2 and its direction. So that means I need to take this right here and I need to factor out a square root of 2. So factoring out a square root of 2 means that this needs to be divided by square root of 2. So this one's going to be 1 over the square root of 2. 0 divided by square root of 2 is still 0. And then this one would be 1 over the square root of 2. And if you multiplied it back in, you would get this back again, the velocity vector, but now it's written as a product of its speed and its direction. Okay, couple more examples. So how about the function e to the t, e to the 2t, e to the 3t? So now write this as a function. I prefer out the n in function with x, y, and z. Well, with the very first one, I could use the idea that sine squared plus cosine squared equals 1. But notice that each one of these has e to the t in it. So first thing I'm going to do is rewrite this. The first one I can't really simplify, but e to the 2t can be rewritten as e to the t being squared. Because when you have an exponent raised to another exponent, you multiply those two, and that's the 2t. And then here it would be e to the t being cubed. So this could be x. So actually, I would have that x is equal to e to the t, and then y is equal to x squared, and this is going to be the z part is equal to x cubed. And then I don't really have a way of getting rid of this e. I guess I could say take natural log of both sides. And so then this one would become y equals the natural log. Oh wait, no, I can't rewrite that one. That's about as far as I can go with this one, because there's no real identity for like e squared plus e cubed equals 7 or something like that. So that's as far as we could go with that one. That wasn't really the main point of this one. The main point of this one is find the angle between the velocity and acceleration vectors. In other words, find the first derivative, it's going to be a vector. Find the second derivative, it's going to be a vector. At the point 1, 1, 1. So again, this is telling you what x, y, and z equals. So if this equals a 1, that's because it's e to the 0 that equals 1. Aquí también y aquí también. That means that t must equal 0. So this is just a sneaky way of saying when t equals 0. All right, so we need the first derivative. So r prime is going to be the derivative of e to the t is e to the t. The derivative of this will be e to the 2t, but then because of the chain rule, times 2. And for the third component, it's going to be e to the 3t, but then because of the chain rule, times 3. And then plug in the 0. So when you substitute the 0, this is going to be e to the 0 is 1. This will be e to the 0 is 1 times 2. And this one will be 1 times 3. So there is the velocity vector. Now for the acceleration. So now we need the second derivative. So the derivative of the derivative of e to the t is still e to the t. Then when you take the derivative of this, you're going to have to do the chain rule again. It's going to bring another 2 down. So that's actually going to be 4 times e to the 2t. And then this one is going to have another 3 brought down when you do the chain rule. So then it's going to be 9 e to the 3t. And then plug in the old 0. So the acceleration vector at 0 will be e to the 0 is 1. This will be 4 times 1, and this will be 9 times 1. Now find the angle between these two vectors. So I'm going to use the formula that says cosine of the angle is equal to, now do the dot product. So 1 times 1, 2 times 4, 3 times 9, and then find the length of each vector. So it's going to be 1 squared plus 2 squared plus 3 squared inside a square root. And then also 1 squared plus 4 squared plus 9 squared inside of a square root. And then take cosine inverse. So you could simplify it if you want to first of all, but since I'm going to type it into the calculator anyway, might as well just do it right now. Take cosine inverse of, the numerator has 1 plus 8 plus 27, put that in parentheses, divided by, and I should put this in parentheses, the square root of 1 plus 4 plus 9. And then another square root that has 1 plus 16 plus 81. And right now it's in radians, so the angle is equal to 0.238 in radians. If we want degrees, just change this to degrees, second quit, put second enter to get it back, or it's 13.613 in degrees. All right. Those are the examples that I created after looking at the homework. And then I want to just take a look at one. Find the parametric equation for the line that's tangent. So as soon as it says tangent, that means we need to find the derivative. And they were kind enough to just tell you t equals 0. So we need the derivative. So they're using ijk instead of the component form. So let's see, the derivative of sine is cosine. So this will be 5 cosine of t, and that's for the I component. Then the derivative in here is going to be 4t squared. Oops, just kidding, 4t cubed. And then the derivative of cosine is negative sine, so it's going to get rid of this negative, plus 6 sine t. That's for the j component. And then the derivative of this one, so the derivative of the e to the 2t is still e to the 2t, but the chain rule is going to put an extra 2 down there. So then it's going to be plus 8 e to the 2t for the k component. And then plug in 0. So let's see, cosine of 0 is 1, so that means this is 5 times 1. If you plug in a 0, that will be 0, and also sine of 0 is 0, so that means that the middle one is 0. And you could either just not write it, or you could say orange juice. And then e to the 0 is 1, which means that it leaves 8k. So this is our vector. Now we also need the point. What is the point? That's what I've been wondering. What's the point? The point is when you plug in 0, right here, sine of 0 is 0. So that's going to be 0 times I. When you plug in a 0, that is 0 to the 4th. Cosine of 0 is 1, so that leaves negative 6 for the j. And e to the 0 is 1, so that leaves 4 times k. So this, we consider it a point. Even though it's a vector, it's basically like the vector is sitting out here pointing to this point as the curve goes through that point. And then this would be the tangent vector. So now find the equation of the line and putting it in this form. So x equals something times t plus something. Y equals something times t plus something. I wish I had this part that I could just cut and paste like it just automatically came out, but I actually have to write it each time. It's okay, it's fun. And then in front of t, that needs to be the vector 5, 0, 8. 5, 0, 8. And over here needs to be the point. What is the point? The point is 0, -6, 4. And now we're done with the first section of chapter 13.